So, what truly makes up the whole universe? Is it cells? Molecules? Atoms? Or even at a small scale, quarks? Well, this theory will answer this question, string theory. A theory which states that fundamentally, the whole universe is made out of these vibrating strings. But before we dive into the theory, we must know what a theory means. A theory is an idea that is strongly supported and extensively accepted in the science community, or whatever community it is, but it can't be a law. So, string theory, it's a very complex theory that has a bunch of goofy equations that neither you and I could comprehend. But I'll try my best to simplify it as much as possible. But you know me, I love to write a whole novel. And if you know me well, I wrote a 32 personal narrative. But writing aside, this is a very complex theory. So it'll be broken down into string theory's different goals, and we'll go in depth on each of them, as well as many other things.
You can't touch this.
String theory's main goal is to be the theory of everything, and now every single thing is all because of this theory, and tries to unite quantum mechanics and general relativity, because they have issues mathematically, maybe physically. But string theory is mostly about strings, and how different particles arise from different vibrations, which come from different energy levels that are being applied to them. A string exists in the quantum scale, or in the very small scale, and is a one-dimensional object. And if you don't know what that means, imagine a square, but then you subtract its width, so now you have one line of length. There are two different types of strings, an open and closed string, both of which can do interactions upon themselves. An open string is a string with ends that don't touch each other, while a closed string describes that oppositely. But back with the different vibrations and different energy levels, which are important and can determine the properties of each particle, which can explain gravity at a quantum scale, the graviton particle, but that has its own time of discussion. So, how do these particles form? Strings, open or closed, can possess specific properties depending on the frequency of vibrations. The more frequent the vibrations, the more energy it has. And this can also relate to the mass, because from Einstein's famous equation, E equals mc squared, energy can affect mass, so the more energy means more mass. But since there could be thousands of particles that could be created just because of this, we could organize the more important ones into the standard model.
What the hell?
A particle physics theory that correlates well with string theory. It can help solve one of string theory's biggest problems with gravity and general relativity. But please don't let this table intimidate you. It's just a table after all. But the standard model organizes these particles into bosons and fermions with a subgroup of leptons. The mass of these particles are measured in GeV or MeV, giga electron volt and mega electron volt. And while all these sound like very nerdy words, it's pretty easy, at least for me. Anyways, bosons are the particles that mediate 3 of the 4 fundamental forces of the universe. Think of a particle having different superpowers, but these 4 fundamental forces are nuclear force, weak force, electromagnetism, and gravity, the force that is like no other. If you don't know what these forces are, here's a quick definition. Strong nuclear force is responsible for keeping the atom's nucleus together, while weak nuclear force is responsible for radioactive decay and the notorious atomic bomb. Electromagnetism is about having to deal with electric and magnetic relationships, but mostly about the different waves it includes. Gravity is, well, gravity, pulling everything into itself. But what mediates or does these forces? Just a reminder that we're talking about bosons. Well, these bosons, the photon, who has the power of electromagnetism, gluons, which there are 8 of them, which does the strong nuclear force, and 3 other bosons called Z, W+, W-, bosons which does the weak nuclear force. But the real question is, who does gravity? It's been speculated that another boson, the graviton, exists, but so far its existence hasn't been confirmed yet. As many scientists work their way, because adding the graviton could unify all the forces into one and further explain what the one force was like in the very beginning of the universe. All of these bosons can also be called gauge bosons too. There's also this fifth boson called the Higgs boson, which mediates no force but provides mass to other particles via Higgs field, but we won't go deeper than that. Fermions, on the other hand, are building blocks of subatomic particles in the atom, which are comprised of 6 different types of quarks, as well as 6 other leptons. They are organized into 3 generations, which means that each generation, the particle is heavier than the last. I honestly don't know why there are 3 generations, nor do the scientists do, but it has been speculated they'll have to do with supersymmetry, a topic that we'll dive into soon. And in the conclusion of this part of this video, bosons have the power of 3 of the 4 fundamental forces of the universe, with graviton being a mysterious and elusive particle that we must find, as well as the Higgs boson giving mass to particles. Fermions are responsible for creating the subatomic particles of an atom, like an electron or a proton, through quarks and leptons. Well, overall, congratulations. You've completed the most important but exhausting part of the video, so good luck with the next topic. In the last chapter, we've mentioned supersymmetry, and well, what the heck is it? Supersymmetry, or SUSY, S-U-S-Y for short, is a concept that came from string theory and helped more to solve its issues with one of string theory's ideas and many other things. First, what is symmetry? Symmetry is basically dividing an object in half and both sides will be the same. Easy, right? Well, not really. In the late 1960s, string theory had a different name, the bosonic string theory. Just like string theory, with strings of different vibrations interacting themselves and between other strings, the bosonic string theory is a mathematical mess and hardly describes our universe. A few problems was that mathematical results required way more dimensions, as in 26 dimensions plus time itself. String theory is supposed to obey Einstein's laws of special relativity, which required 4 dimensions being up, down, left, right, forward, backward, with one other dimension of time. Currently, this has only been reduced to 10 dimensions, including time, as Andrew Neveu and Joel Shirk solved the problem dealing with bosonic string theory. But it still remains a problem today, as it can't be a valid theory since string theory also has to unite with quantum mechanics and general relativity. Most of these dimensions have been theorized to be curled up at various quantum scales. There is also another major problem with the bosonic string theory, and it was that fermions cannot exist. If you remember from the last chapter, fermions are responsible for creating protons, neutrons, and electrons, which make up atoms and ultimately matter itself. A mathematical mess indeed. Luckily, physicists didn't want string theory to be easily invalidated just because of that. Supersymmetry saved string theory by theorizing that fermions and bosons are related by doubling the particles. For every boson, there is always a corresponding fermion, and that boson can become into a fermion without changing the results, and vice versa, which shows that they relate to each other and ultimately allowing fermions to be in string theory. So, supersymmetry, or SUSY, is basically doubling the particles of the standard model, and those particles are what we need to find from the LHC, or Large Hadron Collider, which is a very, very, very long machine that is used to create particles from putting other particles at 1/3 of the speed of light and colliding them. But back with supersymmetry, it's like looking at another universe, except it's for particles. Particles that have been supersymmetrized, or sparticles, very odd name, eh? But let's say our fermion has been supersymmetrized, and let's take an electron as an example. So its supersymmetrized partner's name is named Selectron. You basically add an S for a fermion's partner in the beginning of their name. While for bosons, it's like adding an INO, eno, in the end of their name. For example, a gluon is gluino. So, what about the elusive graviton particle? Of course, it'll be called the gravitino. But one big mathematical problem arises. And this didn't come from me because I don't want to learn this math, but from the book and the internet. But in all, when putting the graviton or gravitino into general relativity, infinities will come. And infinities are a curse in physics because they're immeasurable. Infinity is not a number. It goes on forever, and there's no way of measuring something that goes on forever, because of course it will never end, and there will be no specific answer. There are ways to tame infinities and make them measurable, and that's called renormalization, and it's applied to equations when infinities arise and make them measurable. But gravity, especially at a quantum scale, cannot be renormalized because of math and science. Well, that was big, but we have more to go on. On the next chapter, we'll discuss string theory's controversy and as much as string theory may be hopeful, it has a lot of criticism that just roasts string theory and theorists themselves really hard. It has many problems, such as string theory getting more funding from institutions, not towards other theories that make somewhat sense, because string theory has a lot of problems, and it's a waste of money to be putting in money in failures. When I mentioned about supersymmetry and the LHC, Large Hadron Collider, and the machine itself trying to find partners of the original standard model, it turns out it failed. There were no such thing as electrons or gluinos, and without supersymmetry, string theory will fail to describe reality, as fermions won't exist at all, a building block of matter. But the LHC isn't a waste of money itself, it's the funding that is. Additionally, you can't experiment with the string theory, as it's way too small to be able to test it and do anything with it to prove things, unlike the standard model theory, which has completed the standard model by discovering the Higgs boson, unlike string theory, which fails to do anything like that. Part of the scientific method suggests that in the end of experimentation, you must draw conclusions, and since string theory is incapable of being experimented on, you can't draw any conclusive evidence to share with the world. Additionally, when dark energy was discovered in 1998, which is a type of energy that accelerates the expansion of the universe, and according to HubbleSite.org, while ground-based studies had measured this accelerating period, Hubble's observation of 1997 FF stretched back to the decelerating part of the expansion. This shift between two different eras of the universe, changed from a decelerating universe to an accelerating universe, showed that dark energy exists. While according to Home.CERN, a very important organization, they state, the rate of expansion and its acceleration can be measured by observation based on the Hubble law. These measurements together with other scientific data have confirmed the existence of dark energy.
Wake up! Wake up! Wake up! Wake up! Wake up!
While these quotes may not be supportive as you think, they kinda are, since they come from different important organizations such as CERN, European Council for Nuclear Energy. But both of these organizations confirm the existence of dark energy, which comes at a problem for string theory as they both contradict each other. But since dark energy's existence is confirmed and string theory is not, then dark energy will be a more believable option to choose. And if they happen to be united, like what happened in 2003, then there will be 10 to the power of 500 ways to write this theory out. And we don't have time to do that as it's like an infinity, except it's somewhat smaller than infinity. So, what happens to string theory? Is it right or wrong? Honestly, time will tell. When our technology advances, we will be able to observe the unobservable, create more theories and more observations in the natural world. Other theories like loop quantum gravity theory is a big competitor. But maybe another theory may arise. String theory could be correct, we just don't have the technology to do it. Or investing into those technology could just waste a big sum of money and just proves the theory to be a total failure after all.
Let's go.
Overall, I just taught you some quantum physics and particle physics, as well as string theory. Go and flex to your friends that now you're big brain and you're smarter than everyone else. But jokes aside, it's just a theory. A science theory.